Hi there, my name is Jeremy Krug and I'd like to welcome you back to another chemistry video. In this video we're learning about molecular structure, the shape of molecules, and specifically how to draw Lewis electron-dot diagrams for different molecules. If you're new to my channel, take a look around. I think you'll like what you see, and if you do, go ahead and consider clicking that subscribe button so you won't miss a thing on any of my chemistry videos. As we jump right into this section, I want to talk for a moment about how structure affects the physical properties of an object. I think at some level we understand that. For example, you've seen structures, you've seen pieces of architecture that certainly owe their structure to the way that they're designed. For example, this monument here, the St. Louis Gateway Arch, is basically built as an arch, and the reason it's so strong is because of its structure. There's something about that arch structure that allows it to be very strong and resistant to wind and other forces of nature like that. On the other hand, we know that the opposite can be true as well. For example, this bridge, the Tacoma Narrows Bridge, was built in 1940, and because of the way it was built, it really wasn't made to stand up to the severe winds that it was going to be exposed to. And as a result, just a few months after it was built, it actually collapsed, as you can see right here. So structure is a very important part of how an object is built. And we can learn a lot about an object's physical properties by looking at its structure. And we can say the same thing about molecules as well. Now, in chemistry, we use visual models that we call Lewis diagrams, or sometimes called electron-dot diagrams, or if you want to say the whole thing, Lewis electron-dot diagrams, to kind of predict the shapes of these molecules. And if we're going to draw Lewis diagrams, there are a few ground rules. And the first ground rule is that only valence electrons participate in chemical bonding. You might remember from several lessons ago, we talked about how to count valence electrons, or how to determine the number of valence electrons in an atom. Do you remember how to do that using the periodic table? Well, you might remember, in case you've forgotten, that everything in group 1 over here on the left side of the table has 1 valence electron. Group 2, those have 2 valence electrons. Group 13, these have 3 valence electrons. Group 14 have 4, and so on. Group 15 has 5, 6, 7, and then most of these noble gases have 8 valence electrons. You're going to need to know that as you draw these electron-dot diagrams. So in this video, we're going to get a lot of practice drawing these electron-dot diagrams. And so if you're following along, go ahead and draw these along with me and use the periodic table. That way you feel very comfortable when it comes time to draw these on your own. Now we're going to start with a fairly simple molecule. We have fluorine being bonded with chlorine, and honestly, probably the simplest way to draw a Lewis electron-dot diagram is just to draw the two symbols of the atoms right next to each other like this, F next to Cl, and then we're going to assign the valence electrons based upon the number of valence electrons each atom has. So we can look at the periodic table here and see that fluorine is right here, and so it has 7 valence electrons. So I'm going to put 7 dots around the fluorine atom, just like this. Now, notice that electrons tend to be in pairs, so I'm going to try to pair these up as much as I can. Now, the next atom that I want to look at is chlorine, and chlorine is also a halogen. It's in group 17, right there. So it has 7 valence electrons as well. So I'm going to try to pair these up over here as well as I can with the 7 dots around the chlorine. Now you might remember way back in that chapter about electrons, we said that every atom tends to be most stable when it has 8 valence electrons. That's called the octet rule. And so we're looking at this structure that we've just drawn here. Does every atom have 8? Now I would say that yes, it does. In fact, I see in the middle here we have a shared pair of electrons right there. And what that means is this fluorine atom over here can lay claim to both of those electrons in the pair and claim it as its own, so it can say that it has 8. And then chlorine over here can do the same thing. It can lay claim to both of those electrons in the shared pair and say that it has 8 as well. So both of these atoms have an octet. Now, to draw a Lewis electron-dot diagram, we need to replace the shared pair with a line. And so when I draw the line, it looks like this. And so this is the Lewis electron-dot diagram for this molecule. Now, like I said, this is a fairly simple example. We're going to kind of go up in intensity as we do some of the future examples here. But that's the basic idea as to how to do a Lewis electron-dot diagram. Let's try another molecule here. Let's try carbon tetrabromide. And on a lot of these molecules, we're going to find that there's one atom of a certain element and then multiple atoms of a different element. And so the way that you draw those diagrams is you put the atom that is alone as the central atom. So in this case, carbon is going to be the central atom. So I draw that in the middle, and I'm going to arrange the 4 bromine atoms around it. So we're going to assign the dots to each atom, just like we did in the last example. Now, in all the years I've been doing this, I've found it's really helpful if we start with the outside atoms and work our way into the center at the end. Do the outside first and do the inside last. I found that that helps me to avoid mistakes. I think it'll help you too. So we'll start with these bromine atoms, and we can look at the periodic table and see that bromine is a halogen just like the other ones were. And so that's going to have 7 valence electrons. So I'm going to put 7 dots around each of the bromines, 7 around that one right there, 7 around this one, 7 around that one, and 7 around that bromine right there. So that's a total of 28 dots. And like I said, I start with the outside and work my way in. That doesn't just apply to the actual atoms, that applies to the individual dots. Notice that I put the dots on the inside part last. You'll see why I did that in just a second. Next we have the carbon atom, and we can see where carbon is on the periodic table right here in group 14. And so it has 4 valence electrons. I'm going to try to pair those up as well as I can. So here's 1, 2, 3, 4. And once again, I'm going to ask the same question as I did before. Does everything have 8? And I think it does. I think every atom here does have 8 because the bromines all have 8 now thanks to the shared pairs, and the carbon does as well. In fact, I can see that we have a total of 4 shared pairs in this molecule. So that is the basic structure here. So to draw the actual electron-dot diagram, I need to replace those shared pairs with lines to represent the covalent bonds in the molecule. So the finished Lewis electron-dot diagram for carbon tetrabromide is going to look like this right here. Let's try another example. Let's try carbon disulfide. Now, once again, you can look at this molecule and hopefully see that the central atom is going to be carbon. So I'll put carbon in the middle, and then we have 2 sulfur atoms. So I'm going to arrange the 2 sulfur atoms, one on either side of the carbon. And like always, I'm going to start with the outside and work my way in toward the middle. So we'll start with the sulfur here. We look at that on the periodic table, and here's sulfur right, where's sulfur? Right there. It's in group 16, and so it has 6 valence electrons. So let me put 6 dots around that sulfur there, and 6 dots around the other sulfur right there. And so we can look at carbon, and we see that carbon is right there, and it has 4 valence electrons. So I'm going to put 4 dots around the carbon just like this. And once again, I'm going to ask myself the same question as I did before. Does everything have 8? And as I look at it this time, I'm going to have to say no. The 2 sulfur atoms do seem to have 8 the way that I've drawn them. However, the carbon only has 4. So that means I'm going to have to move some of these dots around so that everything has 8. Now, one thing I could do is I could drag a pair of sulfur electrons from the left side over here into the middle, just like that. Okay? Now, the sulfur on the left side here still has 8, but the carbon in the middle is up to 6 now. So I'm getting closer to carbon having an octet. Now let's do the same thing on the other side of sulfur. If I take this pair of electrons on sulfur and drag this over into the middle like that, now I have 8 on every atom. So everything has a perfect octet. Now I want you to notice here that we have a total of 4 shared pairs of electrons this time. We have 2 shared pairs right there, and we have 2 shared pairs right there. So that means that when we draw our finished Lewis electron-dot diagram, we're going to need to have 2 lines in each of those positions. And so our finished diagram is going to look like this. And those double lines represent double bonds. And if you had to guess, would you say that a double bond is stronger than a single bond or weaker than a single bond? Well, hopefully you would say that a double bond is stronger. And as it turns out, it is. Double bonds are stronger most of the time than single bonds. And so this helps us to understand part of the structure and how some of these molecules behave. And so here we have a good example where there's a double bond in this molecule. Let's move on to another molecule. Let's try sulfur dioxide this time. And once again, since we have only one sulfur atom, I'm going to put sulfur in the middle as my central atom, and we'll arrange the 2 oxygens around it, kind of like that. And once again, I'm going to start from the outside and work my way toward the middle. And we look at the oxygen atom, and oxygen is right here. It has 6 valence electrons, being in group 16. So I'm going to put 6 dots right there, and I'm going to put 6 dots on the other oxygen as well. And next, I'm going to look at the sulfur atom, and sulfur, of course, is right underneath oxygen on the periodic table, so it has 6 valence electrons as well. So I'm going to put 6 around the sulfur right there. And once again, I'll ask myself the same question as before: does everything have 8? And it looks like the oxygens have 8, but the sulfur only has 6 valence electrons the way it's drawn here. So once again, just like before, I'm going to have to move some dots around so that everything has 8. So I'll do kind of like I did before, and I'll move a pair of dots from the outside of the oxygen there to the middle, just like that. And so now I can look at this structure, and it looks like everything has 8 now, doesn't it? Now, in this structure, it looks like I have one single bond, and I have one double bond right there. And so when I draw my finished Lewis electron-dot diagram, I'm going to draw one single bond here on this side. I'll draw a double bond on the other side, and I have this unshared pair, or this lone pair as it's sometimes called, hanging out on that sulfur right there. Now, this looks like a very good diagram here, but I have a question for you. Let's say that we had this question on a test or a quiz, and instead of drawing that structure right there, you drew this structure right here. Do you think you should get credit for that? Now, as you look at that molecule, I think you'd probably say, yes, you should get credit. It's basically the same thing, isn't it? Except it's just kind of flipped around. We have the double bond on the other side. Everything else seems to be pretty much the same. And this is correct. It is absolutely correct to put either of those molecules on your quiz or your test. This is something that we call resonance structures. And this is where you have 2 or more Lewis electron-dot diagrams that are correct, they're acceptable, and they're fine for the same molecule. And notice that these are not exactly the same molecule. It's not like you can superimpose one on the other. They're kind of like your left hand and your right hand. They're not the exact same thing, are they? You can't actually superimpose your left hand onto your right hand no matter how much you try. They're basically mirror images of each other. And so that's kind of like what these resonance structures are in this case. They are mirror images in this case, and they are both right. And if you put either one of these on a quiz or a test, that would be just fine. So realize that we have resonance structures for a lot of these molecules, more than one correct answer. Now let's try another molecule. Let's try the nitrate polyatomic ion this time, NO3, with a negative charge. Now once again, we're going to put the nitrogen in the middle since it's the central atom. There's only one of that. We have 3 oxygens. I'm going to arrange them kind of around the nitrogen just like I did before. And now I'll start adding in some dots. And so I'm going to start with the oxygens and then work my way into the middle. So oxygen is in group 16, and it has 6 valence electrons. So 6 dots for each of these oxygens, that one there, 6 dots for this one, and then 6 dots for that one there. And then nitrogen, looking at the periodic table, has 5 valence electrons, being in group 15. So I'll put 5 dots around the nitrogen, just like this. Now, I need to put one last thing on here. I want you to notice that nitrate is a charged particle. It has a negative charge. Now, like you might remember back in the chapter about ionization and electrons, if something has a negative charge, that means that it's gained 1 electron. Well, that's kind of what we have here. Since this has a negative charge, that means we have to add in 1 bonus electron somewhere in this structure. Now, do you see a good place where we could add in that 1 bonus electron? Well, I do. There seems to be a really good place for an extra electron right there. So I'm going to put that extra dot in. And now I have enough dots to make this work. Once again, I'll ask myself the same question as before. Does everything have 8? And as I look at the structure, the oxygens do, but the nitrogen only has 5, the way it is drawn here. So I'm going to move a pair of dots, maybe from the outside of this oxygen into the middle, just like this. And now everything has 8. The oxygens have 8. The nitrogen atom has 8 as well. So now we can start counting up the bonds. It looks like we have a double bond and we have 2 single bonds. So a double bond here on the left side, and then we have 2 single bonds over there. So when I draw the Lewis electron-dot diagram for the nitrate ion, I'm going to draw it like this, with the 1 double bond and the 2 single bonds. And since this is a charged particle, I need to draw its structure in brackets with the charge drawn out there to the side. That way, if someone looks at this, they'll realize, this is a charged particle, this is an ion, and it's not like a molecule of nitrogen trioxide or something like that, because that's not exactly what this is. This is an ion. Let's try another one that's similar to this. Let's try the nitrite ion this time. It works very similarly. The nitrogen is going to be in the middle with the 2 oxygens surrounding it. And once again, the oxygen is still going to have 6 dots, so 6 dots for both of those. The nitrogen still has 5, so I'll put the 5 dots for the nitrogen. And this is a polyatomic ion. It carries a -1 charge, so I'm going to add in that bonus electron just like I did before. And now, once again, the question is, does everything have 8? And it's kind of like we had before. The oxygens both have 8, but the nitrogen does not. So I can drag a pair of electrons into the middle there, and now I have everything with 8. So looks like, once again, I have a double bond here and a single bond. This time I have an unshared pair, or a lone pair, hanging out on that nitrogen atom there in the middle. So when I draw the finished Lewis electron-dot diagram, I'm going to put the nitrogen in the middle with the double bond and the single bond, and then that lone pair on the nitrogen. And we need to put brackets around this with the negative charge off to the side to show that this is an ion. It's a charged particle. This is not a molecule of nitrogen dioxide. Let's try one more example together here in this video. We'll take a look at the ammonia molecule, NH3. So we'll put nitrogen in the middle, and we have 3 hydrogens here. I'm going to arrange those around the nitrogen. So once again, we'll start with the outside and work our way in. The hydrogen is in group 1 right here, and the hydrogen has 1 valence electron apiece. Hydrogen has only 1 electron shell, so it's going to be stable with 2 electrons, not 8. So I'm going to put 1 dot for every one of these hydrogens, arranging that in the middle there. And then the nitrogen is going to have 5 valence electrons, just like it always has. So 1, 2, 3, 4, 5 there for the nitrogen. So that's a total of 8 dots here. Now, once again, does everything have the correct number of dots? Well, yes, it does, right? Nitrogen has 8. It's trying to get an octet. The hydrogens are trying to get 2. So they're both stable with 2 there. So once again, with this molecule, it looks like we have 3 single bonds. We have 3 shared pairs. There's a shared pair here, a shared pair here, and a shared pair here. So whenever we draw the finished Lewis electron dot diagram for ammonia, we're going to draw it like this, where we have 3 single bonds, and then that lone pair, that unshared pair, hanging out on that nitrogen atom. So this is the structure for ammonia. If you learned something from this video, if you'd be kind enough to slam that like button, I would really appreciate it. And don't forget to subscribe if you haven't done so already. That way you won't miss a thing on my chemistry channel. Hey, my name is Jeremy Krug. Thanks for watching, and I hope to see you in the next video where we'll learn some more chemistry together.